The magnetic absolute encoder uses electromagnetic induction for precise and stable position and angle measurements with strong anti-interference. It ensures faster, more accurate control and is widely applied in industrial automation, electronics, medical devices, and aerospace. Geehy's magnetic absolute encoder solution, powered by the industrial-grade APM32F103 XBMCU, offers high precision, low power consumption, fast communication, and a compact design. This solution uses the industrial-grade mainstream APM32F103 XBMCU with an ARM Cortex-M3 core and up to 96 MHz frequency. High-speed UART with a maximum communication rate of 4.5 million bits per second, supporting encoder protocols of 2.5 million bits per second or 4 million bits per second. High-speed SPI with a maximum communication rate of 18 million bits per second for efficient single-turn encoder chip data exchange. Low power modes, with current as low as 12 microamps in stop mode and 5 microamps in standby mode. Compact 6x6mm QFN36 package, minimizing design space while reducing BOM costs. Operational temperature range, -40 degrees Celsius to 105 degrees Celsius, ensuring adaptability in complex environments. Geehy's high-end magnetic absolute encoder solution operates with a voltage of 5 volt plus or minus 0.25 volt and provides excellent performance in applications requiring 16 to 21-bit angular resolution. High precision provides 17-bit single-turn resolution with angular accuracy greater than plus or minus 0.5 degrees before calibration and greater than plus or minus 0.07 degrees after calibration. Low power consumption supports 16-bit multi-turn data with a static average current greater than 20 microamps and a 1,100 mAh battery life of over 5 years. High communication speed RS485 communication rate of 4 million bits per second for faster, real-time data transmission. Compact design features a PCB diameter of just 35 mm, ideal for servo motors with a 40 mm flange. Quick deployment eliminates the need for single-turn data calculations and compensation algorithms. In this system, the APM32F103 XBMCU uses the SPI interface to retrieve single-turn position and alarm data from the chip. It reads the states of 2 tunnel magnetoresistance switches via GPIO, calculates turn count and stores, retrieves data using I2C. It communicates with the main device through UART using the encoder protocol and monitors battery and power voltages via the ADC for fault alarms. The MCU's flash page erase, 1 kilobyte and 16-bit programming time are under 2 millisecond, enabling flash to function as simulated EEPROM for data storage and retrieval. Next, we will conduct real-world operational tests. The system includes a drive motor with a built-in 23-bit high-precision absolute encoder for stable speed, connected coaxially to the load motor via coupling. The load motor features a magnetic absolute encoder based on the APM32F103 MCU, providing precise angle feedback to the control system, which adjusts parameters for enhanced control accuracy. First, we conduct a speed fluctuation test, setting different speeds, starting the motor, and recording the waveforms and speed differences at 50 revolutions per minute, 1,000 revolutions per minute, 3,000 revolutions per minute, and 6,000 revolutions per minute. Then, we calibrate the encoder and record the waveforms and speed differences at these speeds, comparing the 2 sets of data. The comparison clearly shows that the encoder's speed fluctuations are significantly improved after calibration. Next, we test the accuracy of the number of turns. We sample data using the upper computer to evaluate the accuracy of 2 motors running at 6,000 revolutions per minute with different encoders. When the drive motor is stationary, the 23-bit optical absolute encoder shows a single turn position of 5949092, which corresponds to 255.307 degrees, with 0 turns. The load motor, using the 17-bit magnetic electric absolute encoder based on APM32F103, has a single turn position of 72408, corresponding to 198.875 degrees, with 0 turns. We set the drive motor speed to 6,000 revolutions per minute, close the switch, and the motor starts rotating. As the motor rotates at 6,000 revolutions per minute, both the drive and load motors' single turn positions and turn counts change. To verify the encoder's ability to accurately record the turn count despite main power loss, we perform 2 power-off reconnection operations. Afterward, we stop the motor and record the final single turn positions and turn counts. The current single turn position of the drive motor is 5447235, corresponding to 233.77 degrees, with 2,717 turns. The current single turn position of the load motor is 80250, corresponding to 220.413 degrees, with 62,819 turns. Since the drive motor rotates forward and the load motor rotates in reverse, the load motor reversed by 65536 subtract 62819 equals 2,717 turns, matching the forward rotation of the drive motor. The single turn position difference for the load motor is 220.413 degrees. Subtract 198.875 degrees equals 21.538 degrees. And the drive motor's position difference is 255.307 degrees. Subtract 233.77 degrees equals 21.537 degrees, indicating that the turn counts and angle information for both motors are consistent. Finally, we conduct a power consumption test, measuring the encoder's consumption at 0 revolutions per minute and 6,000 revolutions per minute. In a stationary state, the average power consumption of the encoder is around 19 microamps, which, with a 1,100 mAh battery, provides a service life of over 5 years. At 6,000 revolutions per minute, the average power consumption is about 40 microamps. In practical operation, Geehy's magnetic absolute encoder solution achieves high-precision motor control with lower power consumption. That concludes our demonstration. Thank you for watching.